Okay, let's start. Okay, can people on Zoom hear me?
Yes, I can hear you.
Great. Okay. So one thing I want to do is I'm going to give you one extra day to do the homework because we're going to get everything you need for the homework done on Monday. But some of you may want to come by and ask me questions, and I'd rather you have a little more time to come by and ask questions on it. So the homework is initially due on Tuesday. I'm changing that deadline, so it's actually now due on Wednesday. So let's see, we'll get here. I think it's full board. Okay, so homework 1 is due on Wednesday of next week. Instead of Tuesday of next week. Okay. Pretty much after today, you're going to be able to do a lot of the homework, not all of it, but a good fraction of it. You can already start doing a good fraction of it. And so start working on that. I would recommend if you can work together with, try to work it yourself. You know, I think that can be beneficial. Try to do it all yourself, and then get together with some of your friends and try cranking it out. If you have any something, come by and see me. I'll gladly work with you on the homework. You can also talk to Anu. Anu is an absolutely excellent resource. He's one of our senior physics majors and mechanical engineering major. Anything I can guarantee you, anything Anu says is going to be correct because Anu is an absolutely fantastic student. So he's also extremely patient. So he's also another good resource to ask questions on. Any questions? Okay, I want to say one thing about 2 of the problems. So yesterday we actually not yesterday, but on Wednesday. So on Wednesday, we proved that the derivative of x squared, let's say that if y equals x squared, then the derivative was 2x. And the reason I mentioned this is I want you to understand where things come from. And on the homework, I'm going to have you do 2 problems that are going to do a different proof. So on the homework, okay. On homework 1, you will prove that if y equals x to the n, well, let's say the a is a constant. Let's say a is a constant, x to the n. What's the first derivative of that from Calc 1? Yeah, you're going to put on the factor. The a just comes along for the ride. It's a constant. So you put on the n, and you decrease this by 1. You're going to prove that, and you're going to prove the following. that if y equals, let's say, sine of x, the derivative here, what's the derivative of a sine? Cosine. Okay. You're going to prove that. So you're going to actually go through, and I kind of lead you through how to go about doing this. But I want to say one thing, because I think sometimes there's some confusion on the point. Okay, how are you going to prove these things? What's the fundamental definition of a derivative? Always, always, always. Okay, so let's, I need room. Okay, so say df dx is by definition what? You tell me what to write after. Okay, what other, okay, so the limit, I like the x here. I'm not entirely happy with this, delta x, okay? Of what? Of this guy right here. Now, if I were to say draw a picture of that, what would you do for a picture? You do the following. There'd be your f, should be your x. You draw some weird thing like that. You come over here to some x. Not this value of x, the corresponding value of f is this. And if you came over here, some distance x plus delta x away, it would be this. So I've added some delta x and I've come over to here. Like at that point, and the value of f at this point is this. Okay. So this right here is my rise, because I'm drawing this. Is this going to show up? It will. So I'm drawing this guy here. That's my secant line. This is my run. And you're going to say the slope of that green line is what? It's going to be the slope of the green line. Is this rise over run, which is what? It's this value minus this value. So I take this value minus this value. That gives me my rise. And divided by the run value here, which is delta x. And then formally, then what do you have to do to actually get the tangent line here? You have to let this delta x become smaller and smaller and smaller, and then that will be the tangent line then at that point, there, the slope of the tangent line. Does that make sense? Now, as far as this notation here goes, because I think there's sometimes a little confusion on how do you do this. So I'm going to give you a little push on this thing. So how would you use this? To find the derivative of x to the n. So how do you use that expression? How does that work? I want you to, when you take an exam, I'm not going to have you do any of this on an exam, but on homework, I don't mind asking the question. I really want you to understand where things come from at a fundamental level. If you really do, it's going to help you a lot in the future. So how would we do that? What is our function? It's x to the n. So when you have notation like this, I think people get hung up on basically the x in here, so we're saying our function is this. And then I think people have a hard time then figuring out what this is here. Okay? I think sometimes when you see this notation, the easiest way to look at it is the following. Okay? When you have function notation like this, imagine not putting an x in here at all, just putting a parenthesis like this. So how do I write this expression here? That's really my function. What does this notation mean? This notation means whatever I put in this slot goes in here. Okay? It's the same thing when we say this function of x here is the sine of x. What I'm really saying is this whatever goes in here goes in here. So then what would this become then? If I were to do this for this here, so what would that become for this guy here? I'll give you a little push to start you with it. So you have your limit. This delta x goes to 0. What does this guy now here? What would you put in for that? Exactly. Because what it is, this is really when you have a function notation, this is what it means. Whatever goes in this blank spot here, you do this corresponding thing to it. So if I put in x plus delta x here, that means I take x plus delta x and I raise that to the n power. So what goes in here is this, x plus delta x to the n power. This right here, this is my f of x plus delta x. Then I subtract then my f of x. My f of x is this guy. So here's my f of x. And then I divide through by delta x. Okay? And then in the problem, I tell you what to do with this, kind of how to proceed with this. What about the one with the sign? What are you going to do with the sign one? Yeah. So in this one, again, when you have the sign one, it's really f of some parenthesis equals the sign of whatever's in that parenthesis. So what you're really going to have is in the sign of x plus delta x minus the sign of x over delta x. And then I kind of tell you how to go through this one as well. Okay? Again, you know what the answers are? You probably did this in Calc 1. I want to repeat it because I really want you to understand it well. And for those of you who are engineers, eventually you might take a course in computational physics or in kind of doing things with the computer. It turns out if you have to do things on a computer, you really need this fundamental definition of a derivative to actually do anything. You use that definition all the time. Okay? Questions? Okay, acceleration. Okay, so we defined average acceleration. So here's our little car. This is at t1. We said it had some velocity v1. Here's our little wall. Here's our road, like this. So maybe this is us here at Alfred, and we're going down the road. We want to go to Hornell. And so when we get to Hornell, we're over here. This is sometime t2. That has some velocity v2. Okay. How did we formally define the average acceleration? And again, the bar means an acceleration, means an average. How did we formally define this on Wednesday? What was our formal definition of it? Yeah, we take the change in the velocity of the object. Okay, over how long it takes to change. Right, so this is really our v2 minus v1 over t2 minus t1. I thought it was delta x over delta t. That's average velocity. It's really easy to get them confused. Okay? So acceleration is, and again, this is, you have everyday use of that word. If something's accelerating, what's happening to it? It's either speeding up or slowing down. Right? That's how you use the word. You say, oh, look at that car accelerate. What does it mean? It means it can, change its velocity really, really quickly. Okay? So let's make a graph of this. Oh, and what did we say the units are? Meters per second squared. Okay? So let's ask graphically, what is a bar? Graphically. What is a bar? Now, there's something I always tell my students. I say physicists are one-trick ponies. You basically learn something and you beat it to death. You keep on using the same trick over and over and over again. Okay? It just comes in a new variety when you do it. Okay. What did I say that? What do you think this is going to be? Done. That's exactly what it is. Good. So let's make a graph of v versus t. So here's the velocity of the object. Here's the time. I'm just going to draw some stupid curve because I don't know what it looks like. Let's say it's this. That's our stupid curve. Let's actually plot this. So here's T1. And at T1, the velocity is V1. And let's say T2 is over here. At T2, my V2 is over here. So if I look at this equation here, V2 minus V1, what is that? This right here, that's V2 minus V1. It's a difference here. Okay? But that's the same as this difference over here. Right? This is our V2 minus V1. So this is our delta V. So this height here, that's the change in velocity. Where's my friend T2 minus T1? Well, here's T2, here's T1. That's this guy. This is our T2 minus T1. So this is our delta T. So if I take delta V over delta T, that's going to be the slope of that secant again. So here's our secant. Okay. And the slope of the secant that's actually hard to see on the projector. Is the rise, my delta V, over the run delta T. The exact same thing as what we did for average velocity. No variation, just a different quantity. Does that make sense? Okay, again, physicists are one-trick ponies. This is great. So now I can know the average velocity going to Hornell, but what might I want to really know? I mean, the average acceleration going to Hornell, but what might I really want to know? Yeah, I might want to say, suppose I'm here at a very fixed time. What is my actual acceleration at some explicit time right here? Now, I don't want the average. I want to be here and I want to know how fast my car is going, the acceleration of it. So let's ask, how do we find the actual acceleration of the object, let's say of the car, at time t? So I'm going to be right here. We'll call this t. I want the actual acceleration here. So all that stuff we did before with the average velocity, it all comes back here. No variation. So go through that argument again. Okay, why did we do that? So initially, start off, everything you said is correct. Okay, so initially we said, what was the crappy approximation of the acceleration here? Yeah, we said if I want a kind of a bad approximation to the actual acceleration here, I could say a bad approximation for the acceleration here is the average acceleration between these 2 points. So we could say a bad approximation. So a bad approximation to the acceleration at a point is the average acceleration. So we show that to our friend and we say, look, I have a crappy acceleration. Now, what does our friend say? Now go on your thing. Yeah, our friend would say, well, oh, you can actually improve that approximation by taking T1 here and T2 and moving them closer to the point you want. And then use that average acceleration as a better approximation for the actual acceleration. Then you show it to another friend, and what does that friend say? Yeah, move them closer and then closer and then closer and closer. In other words, what do we get? We get the exact same thing we had for average velocity. There's no variation. So let's write that down. So if we take T1 and T2, if we move T1 and T2 closer to closer to our time t value and recalculate the average acceleration. We will have a better approximation to the acceleration at t. Okay. The closer we take it, the better the approximation. So the closer we move T1 and T2 to our value, the better the approximation. Okay? Does that make sense? So now we can formally write what this is going to be. So I can actually say the actual acceleration or what's another word for actual acceleration? Instantaneous acceleration. Okay, we're going to share something here that we're not going to share with anyone else here, okay? We're not going to share how I spell words in this class, okay? How I spell words in this class, there's going to be our little secret, and we're not going to share it with absolutely anyone else, okay? Now, there's many ways to spell. So what you can do sometimes if you get stuck, you can say like instantaneous, like this. Instantaneous. And then you underline it like this, instantaneous. It's important to do that, like that. That's important. Again, we're not going to share how we spell words in this class. One of my colleagues in math, he's no longer here. I wish he was. I miss him a lot. He was complaining. He was teaching a math history course or something. I don't know what. He was complaining that the students couldn't spell Pythagoras or hypotenuse and stuff like this, and he was going on and on and on about how students can't spell. And you know, I didn't make eye contact with him. I just nodded and just. You know, it's important not to make eye contact. You just nod and say yes. Damn students these days can't spell. Yes, yes. That was important. Okay, so the actual acceleration or instantaneous acceleration is the limit, and you finish it up. Okay, so give me kind of a compact way to write that. Delta V over delta T. Like that. Okay, does that make sense? So you have a car whizzing by you like this. If I want to know the acceleration here, what do? When the car is here, I measure its velocity. When the car is over here, I measure its other velocity. I take the difference. That's what this is going to be. The time it takes to go from here to there is really, really tiny. This is delta T, and that ratio there is the acceleration at that point. So what do we formally call this? The whole thing? The derivative of v with respect to t. So this is our dv dt. But what is the velocity? Always, always, always. The xct. So this is the derivative with respect to time, or the derivative of the position with respect to time. So this is the rate of change of the actual slope. What is this quantity here called? What would a mathematician call this, the derivative of a derivative? The second derivative. So the acceleration is this, dv dt, or you can write it like this, a second derivative of x with respect to t. They're both fine. Okay, I'm going to give you one word that I'll give it to you. I'll give you the definition. We're not going to do anything with it. There is something called a jerk, a mathematical jerk. Okay, anyone know what a mathematical jerk is? A really evil math professor. No, what is a mathematical jerk? Yes, of what? Okay, velocity is dxdt. It's how the position changes with time. Acceleration is how the velocity changes with time, dv dt. What do you think the jerk is going to be then? How the acceleration changes with time. So the jerk of something is actually, by definition, it's a change in the acceleration with respect to time. Okay? That's well named. If your acceleration is changing with time, it's going to cause like a jerking motion on your body, quite severe. And that's why it's called the jerk, because of the psychological connotation. Okay, I've never done anything at all ever in my life with jerk. I think if you're doing like rockets and stuff like that, then you actually do have to worry about the jerk. But not in this course. Okay. So let's take into some examples here. How am I doing with time? Great. Okay. Okay. So let's say I have position versus time here. Let's say I have this graph. And I want you to qualitatively find v versus t and a versus t. So make qualitative v versus t and a versus t graphs. Okay. You tell me how to do the v versus t. Here's the thing you said is fine, but tell me why. What is velocity always, always, always? The xct. Did you have a question? Okay. No, okay. So this right here is the xct. Always, always, always. Okay, how do we interpret this? The derivative is what? of the, okay, the secant where it's really, really tiny, so it becomes the tangent line. So your first derivative here is, a derivative is always the slope of your tangent line. So we have to draw tangent lines here. And again, what was the first thing I told you to do to make life easy for yourself? Find the zeros. Okay, where do we have a 0, 1? Yeah, right there at the minimum. So I go here. Here's my minimum. I then graph that slope. Again, this graph here is a graph of the slope. So this is 0. So at that time, I have 0 here. Now what do? I start on this end, and I just work on this end here. So from right here, what do I have? And so I draw my little thing here. I have some steep negative slope. So what do I draw on this graph here? So at t equals 0, I have a steep negative slope. So what do? I come down here and I draw a steep negative slope, that value. So where does that go? Yeah, it goes someplace here. Now what? Let's say I'm here. How does the tangent line look here? Okay, so how would you draw it? It's going to be less than negative than this value, so it's going to go like that. And then what? Yeah, you have to plot that point then. So this has a less negative slope than this guy. So this is down here. So at this time here, remember, this is at the same time. So at that time here, I'm going to come down to something less negative than this guy. Let's say here. It's qualitative. So if I had this here or here, it wouldn't really matter. It's a qualitative graph. Okay. Now I come over to here. Yeah, that's a slight positive slope. So how do I draw that? Yeah, so I'd come here like this. I'm going to have something positive. Then I can go way over to here. What do I have? More positive, so I have that. So I'm going to have something like this. Does that make sense? Now I come down to the acceleration. Now, what is the acceleration always, 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 always? Yes, this is always going to be your dv dt. Meaning it's going to be what? It's going to be the slope of the tangent line on the v versus t graph. So this right here, this is the slope of the tangent line on the v versus t graph. Okay? Okay, so if I'm here, how does my slope look? I have this guy here. That's my slope. So that is something positive, so I have something here. How about as I go along here? They're all positive. How do the slopes look? Yeah, there could be a little wiggle. It's hard to tell, but it looks kind of all the same to me. So as you come along here, the slope here looks the same, slope here looks the same, slope here looks the same. The slope is the same all the way along here, more or less. So I'd have a whole series of dots like this, which are, yeah. I came prepared. Ta-da. Okay. Whoa. Okay, so like that. So the slope here looks like this. The slope here looks like this, all the way up here. So I'm going to have basically the same value here. If I graph this, I get something more or less like that. Does that make sense? Okay. Now, this is positive here. Now, what else did we say the acceleration is? We said it's this, but we said we could also write it as something else. Remember, we said the acceleration is also the second derivative, the position with respect to time. What does it mean to be a second derivative? It's a derivative of a derivative. So if I have this, it's really, right? So what we can do is, let's go back to this graph here, and let's look at how basically the slope changes. So what did we say this is the slope here? This is, it's a negative. It's a negative slope. What is the slope here? Okay, it's still negative, but how does it compare to this? It's less negative. So what's the change? Is it a positive change or a negative change? It's a positive change. Then we go from here, now we go from here. Well, how does the slope here compare to the slope here? It's less negative because they're not zero, so the change is positive. If I come over to here, what's the slope over here? Positive again from here. So what's going to happen here? If you look at the rate of change of the slopes, in other words, if my hand's my slope, let's say this is the slope. I have negative, less negative, zero, positive, more positive. The rate of change of that slope is actually positive. That's why I'm getting this here. The mathematicians give this another name, the second derivative. What do the mathematicians call the second derivative? They do, but they give it another name. But what you said is true. Scooby-Doo would say longevity. You have to learn how to speak Scooby-Doo. Okay. How do you speak Scooby-Doo? You put R's in things. So like, hello. And Scooby-Doo is what? Hello. And then it's always good to then have like end with Shaggy. So like, hello, Shaggy. So this would be, Rebel Raggy. Brilliant. Okay. What rhymes with longevity? Concavity. Okay. So this is also called the concavity. Crazy. Okay. So the second derivative tells you the concavity of that curve. What would be something if it had a large concavity? What would that be? What's the difference between a large concavity and a small concavity? Yeah, so this would be something, this would really have a really large concavity. But the derivative is certainly, the derivative is changing along here, but not really great. If I had something like this, what's happening to that slope along there? It's changing really rapidly. So that second derivative tells you kind of the concavity of that curve. Okay? Does that make sense? Let's try another example, and then we're going to do something we're going to get a lot of mileage out of. With respect to time. Yep, that's what you'd say. Okay. So let's say I had the position of something going as this, t squared e to the minus 4t. So that's the position of something. I want you to find v as a function of time and a as a function of time. Okay, so what would you do? Yep. Yep. So if you want it as a function of time, it's really asking for the actual velocity. So these are derivative questions. So this is going to say v is dx dt. And then the acceleration is what? Second derivative or just dv dt. Okay? What you said is completely correct. So we're going to have to calculate this, and then we're going to have to calculate this. Okay. You tell me, first of all, what would a mathematician say about this? This is a product. So we're going to have to use the product rule. Okay. You do the product rule for me. Take the derivative of the first, the second comes along for the ride, and then plus, now the first comes along for the ride, and then we take the derivative of the second. So the first term is, the derivative of t squared is 2t, e to the minus 4t, so this term just comes along for the ride. Now plus, now the t squared comes along for the ride. What's the derivative of e to the minus 4t? Yeah. So you get minus 4 e to the minus 4t. Okay. That looks a little ugly, so I'd clean that up a little bit. This just looks ugly. Okay. That's my velocity. Questions with that? Tell me how to find the acceleration. This is going to hurt. Okay, so this is our dv/dt. So what do we have here when we do this? How many products do we have? We have two. We have a product rule here. Then we have a product rule here. So this is going to be a big hellacious mess. Okay? Let's do this one. How do we do the product rule on this guy? So the derivative of 2t is 2. Then comes e to the minus 4t. Plus, now this guy comes along for the ride. And the derivative of e to the minus 4t is minus 4 e to the minus 4t. Okay, so I'm done now with this first term here. Okay. Now we have to go to this term here. So we got minus 4, because this is a constant. Now tell me what this guy is. Yeah, so parenthesis, 2t e to the minus 4t. Okay. Oh, like that. Okay. Plus, yeah, t squared, this guy comes along for the ride, and then derivative of this guy, minus 4 e to the minus 4t. There we go. Make sense? That looks a little ugly. Let's make it look a little prettier. Okay, so this would be 2e to the minus 4t. Oh, I can go on, I haven't gone on one of my rants yet. Okay, so notice what the problem is here. Is that we're here in the Science Center, and look at the blackboard space, it's limited. Unlike if we're in Olin. So if you go to Olin, besides being able to find out what your stock prices are when you walk out of the room, you have these enormous blackboards. And what do they put on there? They put their sociology equations on there, their political science equations on there, and their business equations in there. Crazy. Okay, there I've vented. Now I feel better about it. Okay, so let's make this look prettier. So we have this guy here. This guy here. Okay. Okay. So we're working on this term here now. Okay, when we got that. So this minus 4 here, that was this guy here. Okay. And then we took then this guy here. That mess here is the derivative of the t squared e to the minus 4t. Okay. And see, I don't have the space for it. Try doing it both here. A equals 2e to the minus 4t. This guy here gives me minus 8. So I'll get that guy out of here. Minus 8t e to the minus 4t. And I have this guy here. Another minus 8t e to the minus 4t. Then I have this guy here, so I get a minus, making a plus 16 t squared e to the minus 4t. I'd still do one more thing. What would I do? There's one piece of ugliness in there. You could. I'm not going to, but that's perfectly correct. But there's another more glaring thing. Yeah, you have these two guys here. You wouldn't leave it like that. That's kind of a silly way to do it. You'd combine those strings together. So you'd write this as a equals e to the minus 4t minus 16t e to the minus 4t plus 16t squared e to the minus 4t. Right, that's how you'd write it. Oh, you could factor a term out like that, but they won't cancel. Okay. But it turns out there's a part B to this question. Crazy. Part B. Find the average velocity and average acceleration between t equals 1 second and t equals 2 seconds. Oh, actually, no, we're going to do 0 seconds and 1 second. Otherwise, you're going to get a mess. So you tell me how to do that. Why don't you tell me what to do? Okay, there's a really tempting wrong thing here to do here. Don't even write the following down. Tell me what the really tempting wrong thing here to do with this guy is here. So there's a tempting wrong answer. A little bit different. So if you want this, what might you do? You say, oh, I'll evaluate v at 1 second. So I have my expression for v. I'll put in 1 second here. I'll add to that the velocity at 0 seconds, and then do what? If we want the average. Divide by 2. That will give you nonsense. That's not even a term. Because you're taking an average. There's two values there. I'm saying it's a wrong answer. I'm not saying it's correct. Okay. Okay. What this is nothing but a definition. What was our fundamental definition of average velocity? Delta x over delta t. This is just nothing but a definition question. So what you would really have, you wouldn't do any of this. You'd really say that this is, by definition, delta x over delta t. So you'd have what? You'd have x evaluated at 1 minus x evaluated at 0. This right here, this is my delta x. And then I divide that by my delta t, which is what? 1 minus 0. Which I know that's 1, but I'm writing it like that to make so it's a little more obvious what I'm doing. That's what you would do. So what would you have? What was our value of x that I was forced to erase because I'm in the limited Blackboard space of the Science Center? Was it t squared e to the minus 4t? Was that our x? Okay. So what is this guy here? This guy is, yeah, this would be 1 squared e to the minus 1 here, minus, this guy is 0, and that gets divided by 1. So this is just e to the minus 1. What would be the units for this? Everyone agree? Yep. Okay, tell me how to find, assuming we have 2 minutes. Good. Okay, we can actually finish this up. Tell me how to now find the average velocity, frequently called the average acceleration, or the limit that v becomes a. Exactly. So that one we have to do. This is by definition delta V over delta T. Okay, so this is going to be what? This is going to be V at 1 second minus V at 0 seconds over 1 minus 0. What is V at 1 second? Oh, we have to put a 1 here, a 1 here, a 1 here, and a 1 here. It's going to be a mess. Okay, so we're going to get 2 times 1 e to the minus 4 times 1 minus 4 times 1 squared e to the minus 4t. Okay, then we have to divide this by, sorry about that. What happens with limited blackboard space? So this right here, this is our V at 1 second. Now we have to subtract V at 0 seconds, which is what? Yeah, all this was 0, which becomes what? This becomes 0, so this is minus 0. This right here. This is V at 0. Then what do we divide that by? Yeah, 1 minus 0. So if you work this out, you end up with 2 here, e to the minus 4. Okay. Minus, this is 1, so you get minus 4, e to the minus 4 over 1. You wouldn't leave your answer like that. What would you do? Yeah, you wrote this as in minus 2 e to the minus 4. Then you put it into your calculator and get some value. What would be the units for this? This is meters per second squared. Okay, what we're going to do on Monday is we're going to take a very special case. We're going to take a special case of A equaling a constant. And we're going to want to find the position as a function of time and the velocity as a function of time. And these equations you're going to use pretty much for the rest of your life. Have a good weekend. Yeah, you're welcome. Take care. Take care. Yes, Amelia.
Was the velocity
Yep,
equal
yep.
from E equal to negative 14? I'm sorry.
I'm not 18 anymore.
Right,
Okay, so what am I looking at?
Velocity, was
Yep.
it equal to E?
So this is your average velocity. So put a little bar on it.
Oh, yeah,
Yep.
that's true.
So you're doing it. So you're doing the change in V. I mean change in X.
Yeah.
So you basically wherever the T was, you put in 1, and so that gives you that guy. And so that's what you get for this guy. And then it'd be meters per second. And then this guy, you have your bar. Okay, yep. Okay, okay, makes sense.
Okay. Yeah. For concavity,
Yep.
I didn't fully understand.
Okay, so what you have with the concavity thing, it's going to be the rate of change of the slope.
I intuitively
Okay.
get it, but I don't logically.
Okay, so here's the slope here like this.
The rate of change of the slope.
And so you have to look at kind of how slopes change.
Yeah.
So starting from left to right. So here's negative, less negative, a little positive, more positive.
Yeah.
So the concavity for that is the rate of change of the slope is positive. Because it's going from negative, less negative, a little positive, more positive. So the slope is changing in a positive direction.
Okay.
Now for something like this, okay, really, really kind of, bad thing. It's still positive, but you can see it's really changing quite radically.
The rate of change
Okay.
of the slope is much quicker.
So this would have a greater concavity than this guy here.
So this one, is that going to have a steeper acceleration slope?
Well, exactly. That's exactly what it'll be.
Okay.
The acceleration will be greater on it.
Because
Whereas if you went like,
it's shorter.
exactly, over the change.
Okay.
Whereas if you look at something like this is positive, less positive, little negative, more negative.
Yeah.
So now if you look at the change here, you're going from positive, less positive, little negative, more negative.
But it's going to be less slanted.
Yes. So this is going to have a negative, in this case here, the concavity is negative. Okay. And so what the mathematicians do is this is how you kind of sketch graphs by looking at the second derivative, just seeing whether it's positive or negative, because that tells you whether you have this graph, or whether you have this graph.
Okay.
Does that make sense?
Yes, it does. I have to write it down.
This one. Okay,
Okay, and then I'll do some examples.
that's fine. Well, we'll get more examples coming in those.